moving on from our study on AC current and how it varies with time, we can move on to talk about AC circuit. But this time AC circuit here will be connected to either a resistor, a capacitor, or an inductor. So let's move on to pure resistor circuit, in which the accumulator is connected just to one resistor only. So for this case, if we find out that our current is varying with this equation I naught sine omega t here, and we try to measure the voltage across the resistor, what we will see is that the voltage should be varying in phase with the current. Okay, so if our current is I naught sine omega t, then our voltage should be V naught sine omega t. They should be in phase if what you install here it's a resistor. So what does it mean by in phase is if current is increasing, then voltage will be increasing. If current is decreasing, then voltage should be decreasing. If the current reached the peak, then the voltage should reach the peak, and vice versa. If the current reached the trough, the voltage should reach the trough as well. They move up and down in sync. In that case, we call it the I and the V, the current and the voltage are in phase. Okay. Through the derivation that we did in lecture, we determined that V naught, the peak voltage, is equals to I naught R. So from this derivation, we find out that the relationship between the peak voltage and the peak current is just similar to our DC circuit discussion, which is V naught equals to I naught R. The structure is still similar, it's still V equals to IR, just that if now you move it into AC circuit, it will be the relationship between the peak voltage and the peak current. V naught equals to I naught R. Of course, if V naught is equals to I naught R, we can also know that VRMS is equals to IRMS R. You just need to do a bit of substitution, bringing this over, then you prove that this is also true as well. So what we did here is, we fixed our current to flows like this. If we manage to make a current that flows like this across the resistor, we make such a current flowing through a resistor, we'll find out that the potential difference across this resistor over here will be varying with this fashion over here, in sync, in phase. So let's move on to a question to try and test this out. A sinusoidal AC of RMS value 4.00 ampere and frequency 50 Hz flows in a pure resistor. So you have a pure resistor, and for this pure resistor, you find out that there's a current flowing through it, an AC current, and this AC current has a root mean square value of 4.00 ampere. And the frequency of this current is 50 Hz. So means by for every second that has passed, the current actually oscillates a full cycle for 50 times. So it's 50 cycles per second. Okay, so that's the idea of the current that is flowing through this resistor right now. So it's a pure L circuit because they mentioned that it's pure resistor. So let's find the peak current. Peak current, it's I naught. So we're asking for I naught, but well, I believe this question should be quite straightforward, because you learned from a previous video of this relationship. IRMS is equals to the peak current divided by square root of 2. So knowing that, it's a matter of substitution now. So I naught divided by square root of 2. So from here, we are able to find that the peak current is equals to 5.66 ampere. So that's for peak current. So if you look at the next question say, find the magnitude of the instantaneous value of current 6 times 10 to the power of negative 4 seconds after it changes direction. So what does this mean is, we know that our current is actually varying with time. Okay, so let's say it varies with a relationship like this. Okay, should be good enough. So this is, for our syllabus, is always sinusoidally varying. So let's say this is how it varies with time, our current here. So they ask for the magnitude of the instantaneous value of the current. Okay, so they ask for a current at a specific time, but just its magnitude only. So which specific time? they ask for the current at the time when it is 6 times 10 to the power negative 4 seconds after it changed direction. So what does it mean is, if you, let's say you have an accumulator connected to a pure resistance, over here, so your current will be changing direction, right? At one single moment, the current will probably be flowing like this. Then the next moment, you might see that the current will actually change direction. So let's say it might change the other direction, it might flow like this instead. Okay, so our task is to find the moment it changed direction, then you add on this amount of time. Once it changed direction, okay, let me write it down. Once it changed direction, then t equals to 0. Okay, once it changed direction, then time starts. So you can think of it as time equals to 0. And then they ask for the current. The current is what at time when it's equals to 6 times 10 to the power negative 4 seconds. Okay, so what does it mean when the current change direction? It means by before this is like a black arrow going in one direction. After that, if it change direction, then it becomes the yellow arrow pointing in another direction. So for current, right, if you change direction, what you will notice from the current is that it will change from a positive value to a negative value, or it can change from a negative value to a positive value. That's how you change the direction of a current. Because let's say, okay, just let's say when I is equals to 1 ampere, then comparing it with I prime is equals to negative 1.00 ampere. 1 ampere means by it's traveling in one of the direction. Okay, let's say anti-clockwise. Okay, whereas negative 1.00 ampere will be the other direction, which is clockwise. Okay, they didn't really define the direction here, but we know that if you change the sign, you change the direction of the flow of the current. Okay, so when we say once it changed direction, t equals to 0, we are actually meaning points that it changed direction. So the point where it changed direction should be points where it can change from positive to negative, such as the green point I label here, or points like this where it changed from positive to negative, or this third point over here where it changed from negative to positive, or this fourth point over here where it changed from positive to negative. So these points are valid points that we can say that they are the points where the direction changes. So you can call any points here to be t equals 0. So now they ask for once t is equals to 6 times 10 to the power negative 4, what is the current? So they might be asking for a specific time, which you can find probably somewhere here. Okay, once 6 times 10 to the power negative 4 second has passed, then they're asking for this specific time, this specific current over here. Of course, if you want to move it to the other side, you want to start here, also can. Once 6 times 10 to a power of negative 4 seconds has passed, then how much is the current over here? Okay, both of them you should get the same magnitude, just that they are in different direction. Okay, of course it's the same for point over here and the point over here. As long as it's 6 times 10 to the power negative 4, I believe you find the same answer as any other point. Just that they can be in different sign, but we don't really care about the sign because the question asks for magnitude only. Okay, so moving on, the easiest point for us to pick will probably be the point where t is equal to 0, because that's the most easiest point to take care of. So with that said, what we mean is we want to find the current at this specific point. So we know this specific point, time is just equals to 6 times 10 to the power negative 4 seconds. Okay, so this point will be the easiest point for us to find the magnitude of the current. So let's try and figure out the answer. So it's just a matter of substitution. You're finding the instantaneous value of current, which is I, at a specific time, which is 6 times 10 to the power of negative 4. So you write the equation here. you have a I naught sine omega t equation. Your peak current, you have actually found it over here, but I prefer you all to write the exact value because 5.66 here has been rounded up. So writing it like this will be better. Then sine, then you need the omega, but omega is just 2 pi f. You don't have omega, you have 2 pi f, so it's 2 pi 50. That's omega. How about time? You have already agreed to use this time over here. So this time over here is equals to 6 times 10 to the power of -4 second. Okay, so let's sub in everything. Then if you calculate the answer, I believe the answer should come out as 1.06 ampere. So this is the value that you should obtain over here, 1.06. And if you pick other green points, let's say you pick the second green point, then probably your answer will be -1.06. But if you take the magnitude and you modulus the answer, I believe you still get the same 1.06 ampere. So that's how you solve example